In Part 4 of Lecture 3, we will discuss more file commands and inodes. A few more things to say about ls, especially when you're doing a long listing. ls space -l will display a long listing. If you follow it by the name of a file, it will display this information about the file. That includes the normal things you'd see, whether it is a directory or a regular file or another kind of special file. We'll talk more about those later. Read, write, and execute permission for the user, user's group, and the rest of the world. How many links there are, the name of the owner, the name of the group, how large is the file, and when was it last modified. Now, in the case that you see here, the example you see here, you'll notice that I have ls space -l bin/wc. And what you see below is the listing for the binary or executable file wc, or word count. And you can see the information about it. Below that you see ls space -l space period. Now, in a case like this, what it's going to do is it's going to do a list of the current directory. Since I put the D feature in there, it's going to display the information for the directory as it would of any other file, and not display all of the files that are within it. If I had done ls space -l space period, it would be a different story. What I would get would be a listing for all the files within that directory. Lastly, who greater than period is looking to redirect the output of who into the directory, and as before, you'll notice what it does is it tells me that it can't do that. In older versions of Unix or Linux, I could do and use OD to show what the contents of a directory is, and what I would see is that the directory contained the names of the various files and a number afterwards. The number is the inode number. Inodes are a data structure which is, especially at the time when it was created, rather distinctive. The name is short for information node. All the important information about the file, including everything that you see in a long directory listing, is actually stored in the inode, including the length of the file, the device identifier, in other words, the device on which the file is stored, the user ID of the file's owner, the group ID of the group that the owner belongs to, at least as far as the file is concerned, the file mode, is it regular, a directory, a link, a device, and we'll talk more about those a little later, and the permission codes, time and dates of both last modification and last access, a count of the number of links pointing to this inode, and a pointer, in other words, the addresses of the blocks on the disk drive that contain the file's contents. Now, exactly what this means and how we use it is a little beyond the scope of this course. What we see in this example are a few other features that we may take advantage with ls. I started out by printing the date, and you can see that this is today's date, Sunday, November 11th, 2018, at 20:18:36 Eastern Standard Time, which is 8:18:36 p.m. local time today. I'm now going to run it again, this time redirecting the output to a file called junk. Now, I'll do a regular long listing, and you see the protection code, the number of links, that I own the file, my group is users, that there are 29 bytes, and again the time and date when I save the file. Now, lsl-lu will list the file showing the last access time for the file, which is right now. Now, this is different from if I use ls-lc. lc works a little differently, and what that's going to give me is the C time, the time of last modification of file status information. Now, you'll notice that this is going to be right this time because I created the file at this time and that's what it showed. Now, I'm going to use more junk again, and what it'll do here afterwards is ls space -lu, and you can see that the last access of the file was a little later. In this example, you'll notice that I changed the protection scheme. I've given read-only permission to myself, to the group, and to everyone else. And then when I do ls space -lu, you'll see that the last access remains 2019. On the other hand, when I do ls space -lc junk, you can see that I changed this permission, and the last time that I changed the properties of the file was far more recent than that. The reason is because I changed that after the last time I read the file. In the example here, you can see that I've taken a listing of the directory recipes, and I see cookie and pie. Now I'm going to do ls space -lut. Now L we already know gives me a long listing. U gives me a listing based on the last access of the file, and T sorts it by time. Now, given that I have U there, it's going to sort the time using the last access time, not the last time the file was modified, as we see here. At the same time, now I'm going to save date in a file called X, for the heck of it, and ls space -i recipes. What you see here are the two files within the directory recipes, along with their inode numbers. We know the files that we work with by the file name. The operating system, to a certain extent, does know the files by these names, but a lot of the work in manipulating files is done using the inode and the inode number. The links established between the inode number and the name are solely within the directory. ln is a command that allows us to create other links to our file. Up until now, we've always seen the directory listing showing a single link. That is the name of the file as it appears in the directory when we originally created it. When I write ln and then the name of the file and then a new name, I'm creating an alternate way of accessing the file under a new name, or more commonly, under a new directory and a new path. Now let's take a look at an example here. I'm creating a link. I have the file cookie, and I'm going to create a link for it under the name Oreo. And here you can see the long listing for it. The thing that's important to remember when we're using links is that regardless of which name in which directory we find the file, it's still all the same file. So in this case here, I'm going to take the word pie, echo it on the screen, and to standard output rather, and rather than it going into appearing on the screen, it will be written into the file Oreo. Oreo previously had 81 bytes. Now it has 85, as does cookie, because when I echoed it, both names are talking about the same file, both of which have 4 characters more than before. I can now remove Oreo. The additional link is still there, but you'll notice that on cookie, you see the number of links go from 2 back down to 1. Let's summarize these 4 commands. CP creates a new file. So if I write CP cookie Oreo, Cookie and Oreo are two separate files with separate disk storage and separate inode numbers. Any changes I make to Cookie leaves Oreo unaffected, and the same if I make changes in Oreo, Cookie are unaffected. Move can move a file from one directory to another, or I can simply use it just to change the name of the file. But it's the same file before and after, with the same storage and the same inode number. Link is creating a new reference, a new way of referring to a particular file, either in the same directory under a different name, or in another directory where it could be the same name or a different name. In either case, it's the same file, the same storage, and the same inode number. RM is short for remove. It will delete a directory entry. So if there are multiple links to a file, as long as there remains one directory entry, the file still exists and the inode number is still in use. If I delete the last link to a file, then it no longer exists. rmdir allows me to remove a directory as opposed to a file. If you look on the slide, we can see an illustration of exactly how copy and link are different. I start out here with two files, cookie and pie, and I'll create another link to cookie by writing ln cookie Oreo. When I type ls space -li, I get a long listing including the inode number, and I can see that cookie and Oreo are the same file by the fact that they have the same inode number. I'm going to change the protection mode for Oreo by writing chmod -w Oreo. And I can see now that Cookie and Oreo now have all the write permission removed from it. Now below, I can type chmod 644 Oreo, remove Oreo, and copy Cookie. You'll notice that write protection is restored to Cookie. I have it also for Oreo, but you'll notice that Oreo and Cookie now have different inode numbers. Again, I'll take away write permission from Oreo. You'll notice now that Cookie still has write permission for the owner, but Oreo doesn't. I'm going to remove Oreo, and it'll ask me if I wish to remove a regular file that is write protected. I type U, but that doesn't allow me to do it. I do it again now with RM again, and this time I answer Y for yes, and it will allow me to get rid of that file.